I would like to acknowledge Dr. John Retterer at ISR BC, also Dr. Patrick Roddy and Chao Sung Hong at Air Force Research Laboratory, Albuquerque, New Mexico, for many useful discussions, feedback, and comments through this work. So let me start with the presentation overview. The presentation consists of two parts. In the first part, I'll be discussing about the metal oxide samarium cloud experiment, in which NASA launched sounding rocket released samarium metal vapor to create artificial plasma cloud in the valley region of the ionosphere, changing the ambient high frequency propagation environment. I will have results from the experiment to understand the changes made by the samarium metal vapor in the radio wave propagation environment. In the second part, I will discuss the electron density irregularity observations from the joint Air Force NASA Synapse satellite mission, and we will seek to characterize the spatial extent of low latitude irregularities as a function of solar flux. Let me start with Ionosphere 101, which I'm trying to serve as a very brief introduction to the ionosphere. Ionosphere, according to one definition, is the battleground between the Earth's neutral atmosphere and the Sun's fully charged atmosphere, in which the Earth is embedded. It is in this battleground the incoming solar radiation ionize the neutral constituents of the Earth's atmosphere, leading to the creation of stratified plasma layers. In the image in the left, we see the profile of these stratified plasma layers during day and during night. It is very interesting to observe the nighttime profile has lower plasma density as compared to the daytime, for the simple reason that the ionization occurs during the day, and during the night, in the absence of sunlight, the ionization does not occur and recombination of the ionized species occurs. So these stratified plasma layers lead to the many exotic, interesting physical phenomena in the ionosphere, which makes the research very interesting and rich to pursue, as they reflect, refract, diffract, scatter radio waves depending upon the frequency, density, and gradients of the layers. We can look at one mathematical expression right here in the middle for the refractive index, which depends upon that's a very simplified version of the refractive index. A more complete version has more terms. Which, if we simplify the term, it can be reduced to this form, and it depends upon the plasma frequency of the plasma layer and the frequency of the radio wave traversing through the layer. And the refractive index goes to 0 when the plasma frequency of the layer equals to the wave frequency of the radio wave traversing through it. So when the refractive index is 0, that's the condition for reflection. So that leads to the reflection of the radio wave, which enables long distance communication, which makes long distance communication possible. And it is this phenomena which led to the widespread use of HF communication during the Second World War. Later on, the use of HF communication subsided because of the advent of newer and perhaps better technologies in the scientific horizon. But lately, it is gaining increased attention because of few other important reasons, which because of that the newer technologies are not always robust. They don't have coverage in all the regions of the world, and these are easy, cheap form of communication, which can serve as backup means of communication in case of contingency, in case of any emergency, and for few of such regions. And these layers are subject to hydrodynamic instabilities such as Rayleigh-Taylor instability during day-to-night transition and other instabilities in regions of large gradients and strong flows, which in turn leads to changing of the radio wave traversing through them, which is very commonly called as scintillation. And we see in the bottom of the right, in the right bottom, we see a scintillated GPS signal. So that makes it interesting pursuit to pursue, and the motivation in this talk, uh, for this part of talk, is to understand the use of high frequency radio wave system as it has grown rapidly over the past decade, and the performance of these systems rely on understanding the propagation path of the HF energy. The ionosphere frequently represents the limiting factor in our knowledge of the propagation modes. The MOX experiment injected an artificial plasma cloud into the ionosphere to test our ability to understand and model HF propagation effects. So I'm trying to show the video. I'm not sure if it is seen. So do you see this video?
Yes, we can.
Okay, so it's okay, right? So this is the launch of the rocket. That's not the chemical that it injected. That's the exhaust of the rocket. The chemical will be released at certain height.
It's turning red right now. Hey, it's a little bit north south.
So there's the cloud. There is another video of the cloud which keeps changing the color. So in a sense, the rocket created an artificial plasma cloud. This is also known as artificial ionospheric modification. And I'm trying to understand how it would impact the propagation of radio waves traversing through the region. So these are two range time intensity plot of Altair plot, because the experiment was conducted on 2 nights. I showed a video for one night, but the same experiment was conducted on 2 nights. The upper plot is for the 1st May, and the lower plot is for the 9th May. In the upper plot, we see the we see that this is the F region of the ionosphere. This region is changing in altitude. This is altitude, and this is seconds of scan. We see this region is changing in altitude. In the lower plot, this is altitude, and this is seconds of scan, and we can see this is rather stable. So it does not change, the height of the F region does not change as much. So we can say from this that the first night the ionosphere was rather disturbed. It was in motion. In the second night, in the night of 9th May in 2013, the ionosphere was not as much disturbed. In both, we can see the cloud, the images, the signatures of the cloud as well. This is the launch of the rocket. Here is the release. These are the side lobes, and here is the a cloud. This is the trace of the cloud. And so obviously, to understand, for modeling purposes, modeling the second night, the 9th May night, will be easier because ionosphere is well behaved. So we start by understanding the easier one before we seek to understand the difficult one. So this is where the experiment was conducted. It's in Marshall Islands. These are interesting name: Rongelap, Likiep, Otho, Altair. So Rongelap and Likiep are transmitter, TX, and Otho and Altair are receiver. So two transmitter, two receiver makes, I think, four possible paths. Out of these, I will only analyze two paths: Rongelap to Otho, only one receiver. I'll take only one receiver and two transmitters. So that makes two paths. And the release occurred here, middle, midway through Likiep to Otho. Rangelap Otho path is predominantly north-south, and Great Circle path is far from release region. You can see it is far from the release region. Whereas Likiep Otho Whereas Likiep-Otho path is nearly east-west and release point lies nearly on midpoint of the link. Should be ideal for observing the metal oxide layer. So these are the observations made by the HF receiver on the ground. These are before the release. We can see in the y-axis the time. In x-axis we have frequency. So time is the time uh, taken by the wave to travel from the transmitter to the receiver. So this is the F region signature. As I said, the condition of reflection is fulfilled, and thus the signal, the radio wave, is reflected back to the ground. So this is how it is. It is how this is a very clean F region trace, suggesting that the F region is stable, nice, quite. And this is ground wave, direct relay of message from the ground, from a transmitter to the receiver. This is second hop, and this is along Rongela path, and this is along Like path. And this is arbitrarily defined dB. The color represents the arbitrarily defined dB. So this is before the release. After the release, something magical happens, as we expect to happen. So we see additional traces along both the paths. So obviously we can guess, okay, this happened due to the cloud. So this trace, if all of you are seeing the mouse that I am hovering around, so these are the additional traces. So these additional traces, these additional traces are due to the cloud, but we want to understand how exactly were they created. That's the goal of this exercise. For that, I wanted to model. And to model the phenomena, I had to replicate what had happened in the nature. For that, it involved three steps. I needed to assimilate the model ionospheric profile with the observed truth profile, altered radar profile. I need a model ionosphere which resembled the real ionosphere in that night. After I got the model ionosphere, in second step, I needed to plug in the cloud, model cloud. And after I plugged in the model cloud, I had to send the fan of rays, send HF energy, which is very commonly used technique in the field and called as ray tracing. So ray tracing is the simulation of propagation of radio waves through medium of varying reflective indices. So in through these three steps, I sought to model the clouds. There are more details involved in these three steps. Due to the paucity of time, I would not want to go into those, but I will show how I model the cloud. So this is the truth profile of the cloud, the alter radar taken from the alter radar observations. This is before the observations, before the cloud was created, and this is after the cloud was created. So based on this is the cloud. So based on this data, I defined a cloud, and this is how a model cloud image looked like in MATLAB. In a sense, I defined a spherical cloud, a cloud which had very peak density at the center, and as we moved out of the center, the peak density decreased. And this is another image taken during the experiment. So the peak density in my model cloud was at the central pixel corresponded to 7.44 megahertz. The resolution in latitude and longitude was 0.014 degree, which is equal to 1.55 altitude, and we had same resolution in altitude. So it's a three-dimensional spherical cloud that I injected in a 3D ionospheric grid. After which I performed ray tracing, and these are the ray tracing results. These are along Rongelap Otho path. Rongelap Otho, this is Otho, and this was the release point. It was far from the point, and these are the observations. This is the mask layer. This is the extra layer above F region. And how are these? So this is the regular F layer, and these two, this one and this one are the additional layers. So how were these two additional layers created? That was the curiosity, because that would address the our goal to understand the modes of propagation induced by the cloud. So how would that be created? So this is Rongel app transmitter. This is a receiver. So this is a direct path. So that's F trace, direct one. This is the this one, direct one. And the other one is from here to here. That's the secondary F or F region ghost layer. This one. And this can also be created from going to the cloud first and then to the F region and coming back. So these are low elevation angles. These are high elevation angle secondary F traces. As we see in ray tracing, I show them by these blue stars and red stars. So we understand how it is created. It is created by two ways. It involves reflection of from both the cloud and the F region. How about this one? We just call it mask layer. This is created by these low elevation angle rays which go to the cloud and get reflected to the receiver. So these are just direct direct reception, reflection from the mask cloud. So let me try to summarize. This is the regular F region, the direct reflection from the F region. This is direct reflection from the mask from the cloud. This is an additional feature due to the cloud. This is another additional feature of the due to the cloud, which is created in two ways, which involves reflection from both F region and the cloud. So we believe that we understood the observations very well. Like we identified all possible modes of propagation through retracement, and that made us pretty confident about our results. We wanted to conclude. Ray tracing confirms sounder observations to a high degree of fidelity and identifies the modes of propagation. The change in ambient natural propagation environment due to small artificial modification can be successfully modeled. Samarium cloud behave like a divergent lens, resulting in HF voids or shadow zones. So we submitted this for publication, and this has been published in 2017 in Radio Science. I would encourage the audience to look at my paper for more details on our research. So this project was rather ambitious because the initial goal of the project was to seek to understand if the natural disturbances in the ionosphere can be mitigated by such artificial disturbances. So that would have been next step in my research. My advisor was keen to pursue along that line, but due to me not being US citizen or green card holder, the higher authorities did not allow to pursue the pursuit because it was thought to be too sensitive a project for a foreigner to be involved. That made me to change track midway through my PhD, and I started analyzing SYNAP satellite data, in which we try to understand equatorial ionospheric irregularities. So this is the beginning of my second part of the talk. This we try to understand the spatial distribution of equatorial ionospheric irregularities as a function of solar flux. These irregularities are associated with intense radio wave scintillations that impact navigation, communication, and remote sensing systems. While model of occurrence frequency exists, the extent of the regions affected is poorly understood, and the validity of physics-based models of the underlying instability is unknown. So, what are we calling ionospheric irregularities, equatorial ionospheric irregularities? So, this plot tries to illustrate the point. By this blue curve, I am showing ion density as measured by a sensor onboard Synops satellite. Synops was an elliptically orbiting satellite which was in mission from 2008 to 2014. So, so the ion densities are rapidly changing as measured by planar Langmuir probe sensor on board the Synops satellite. To characterize this disturbed region of the ionosphere, there is a parameter called as irregularity parameter, which has been widely used in the literature. So I tried to take the definition, make some simple changes based on my understanding, and apply that parameter to characterize the irregularity in the ionosphere. So the parameter is also plotted on top of the same curve, and we see whenever the blue curve is changing rapidly, the parameter as represented by this red curve also changes rapidly. So, oh, sorry. So, after careful observations and reading previous literature, we decided sigma to be 1.8, 1.2 as the threshold or criterion to identify an instance of irregularity. Following that definition, we created climatological plot of these disturbances. These plots are showing occurrence percentage of these irregularities. In the y-axis, we have month. In the x-axis, we have longitude. So this covers entire globe. So, and this is changing in apex altitude at the magnetic equator, 400 to 500, 500 to 600, 600 to 700, 700 to 800. So we see this occurrence percentage is very high in certain regions, which is equinoctial months, and low around solstice, June, high around equinoctial months, March and September. And this is consistent with previous studies. Like similar climatological plots have been constructed out of previous missions, like other satellites involving other satellites like DMSP, AEE, RockSat. So this confirms the results from previous studies, but there are a few nuanced differences. Uh, but in this study, my goal was to understand the peak height of these disturbances, the peak height at the magnetic equator, because these disturbances are created at the bottom side of the F region of the ionosphere, and they move upwards. As they move upwards, they map along the magnetic field lines. So, how high they rise at the magnetic equator will determine the latitudinal extent of the disturbed region in both the hemispheres. This is very interesting. The height determines the horizontal extent of disturbances. So knowing the peak height at the magnetic equator is critically important. But the measurement, when the satellite makes the measurement, it will not measure the peak height. It will measure whatever it observes, and the observed height most likely is not the peak height. So we pursued a simple thought experiment to deduce peak heights from the observed heights. The thought experiment was based on the physical reality that all higher altitude irregularities at the magnetic equator pass through the lower altitudes beneath them. Like we thought about it, okay, they start at the bottom and they rise above. So, for example, in this example, if there is something at 700, it must have come from, it must have passed through all the altitudes beneath it, and that can be mathematically expressed as this: mg net is observed distribution, is the integration of the true distribution from the from that altitude to the to infinity, because all altitudes, all irregularities evolve from the below. So it's manifestation of that simple physical reality, and this physical reality gives us a way to decipher the true distribution. Just take the derivative. So we ran a simulation here, a very simple simulation. In a simulation, we have the liberty of choosing the true distribution. In a natural experiment, we don't know what the true distribution is, but in a simulation, we can define a true distribution. Okay, I define a true distribution. Let us say there is there are only 40 number of irregularities at the peak height of 700. Only at 700. I have the liberty of choosing it, making it simple. So if since it grows from below, and let's assume that it uniformly disturbs the region below, and let's assume that the satellite uniformly samples all the region beneath it, then the observed distribution will be, we have 40 here, there will be 10, 10, 10, 10. There will be 40. This is, we have made some a few assumptions, valid assumptions. So if I just differentiate these, take differences of these observed distribution, I subtract starting from the last, I make the subtraction, and I get this true distribution. So distribution, out of this initial true distribution, I can get this estimated true distribution. So I succeed in deciphering a peak height distribution from the observed distribution. I am interested in the peak height distribution because it is the peak height distribution which determine the latitudinal extent of the disturbances that arise in the equatorial ionosphere. So there are a few more data processing steps which I have not displayed here. After processing those data, after showing those steps, uh, I deduced these peak height true distribution for per night for 2 periods during low solar activity years and high solar activity years, as the satellite was in mission in operation from 2008 to 2014. 2008 to 2010 data uh, were low solar activity years, and 2011.5 to 2014 were high solar activity years. So I deduced after some data processing steps the nightly peak height distribution. I did so to run another simulation uh, to numerically stimulate synapse experiment. I flew a numerical satellite, an imaginary satellite, through the synapse data that I had. What do I mean by that? I mean, so these are numerical apex altitudes, uh, and these are number of apex altitude pins. So based on those numeric peak height distributions, I randomized the longitude position, and corresponding to those random longitude position, I got the synapse apex altitude, which I made to be the apex altitude of the imaginary satellite that I'm flying. So if the satellite is flying below the numeric peak apex altitude, it detects the irregularity. If it is flying above the irregularity, it misses the irregularity, as is given by the simple mathematical expression. If the satellite apex altitude is below the numeric bubble apex altitude, it will detect the irregularity. That's how I observe the irregularity. Based on this numeric experiment, I get observed distributions during 2 periods, low and high solar activity years. And these very well resemble the initial observed distributions, which I have not included in this talk. So it gave me confidence in the approach that I was following to reduce the peak heights. So it convinced me like my approach to reduce the peak heights from the observed heights is okay. But interestingly, it also revealed another interesting fact because give me a second because I'm not seeing it here. So it also gave me another interesting result in which the in the numeric experiment, the number of odd irregular beings are less than that in the synapse experiment. So it 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 allowed me to conjecture that my imaginary satellite is not observing all the irregularities present in the synapse data. That means synapse also missed good percentage of irregularities existing in nature. So in this numeric experiment, during high activity years, the numeric satellite only observed 44% of the irregularities existing in the synapse data and 28.21% of irregularities in low activity years. Similarly, synapse also might have missed good percentage of irregularities existing in the nature. So that brings the question of efficiency of the space-based platforms such as elliptically orbiting synapse satellite on detecting the ionospheric irregularities. So the observations being made are not the complete truth. There is an efficiency issue. This may not be the very final percentage that we are calculating for the efficiency, but this can be a beginning point to add more complexity to the problem. So, after convincing ourselves with the process of deciphering peak altitude distribution from the observed distribution, we made the peak altitude distributions for different periods, and out of those peak altitude distributions, we got these observations and made fitted line to these observations in which we see the line fit shows that the median of the peak apex height distributions of the irregularities rise from about 491 km at solar minimum to 737 km during solar maximum. This is for the first time in the field that we are putting up a number to the rise of the ionosphere with solar activity. That was our main goal. And we see the tail of this distribution rise rapidly with solar activity as seen in the 90th percentile plot. We also looked up for the peak apex altitude of the irregularities in a physics-based model named as PB mod, and we see the peak apex heights of the irregularities model using the physics-based model fit the observed results very well. So this suggested that there could be something in the PB mod, the model, where we can look for more results to understand the physics, and we process those results, and we learned that conductivity is the key quantity which will characterize the physical process. I'll skip this slide in the interest of time, and I will seek to conclude that the synapse bubble occurrence statistics are consistent with previous work related to this topic. The numerical simulation demonstrates that synapse observes less than half the irregularities during high solar activity years and about 1 by 4 during low solar activity years. The analysis indicates that the median height distribution of bubbles increases linearly from about 491 km at solar minimum to 737 km during solar maximum. These results apply to the minus 80 degree west to 10 degree east longitude sector. In the PB model, the field line integrated conductivity is found to be the key determinant of terminal bubble altitude. Specifically, when the field line integrated conductivity inside the bubble is equal to that of the background ionosphere, the polarization electric field that propels the bubble upwards vanishes and the bubble ceases to rise further. Thank you.
Thank you, Dr. Joshi, for your excellent talk. And then it seems like interesting because it's real application we are seeing every day. So now the discussion section starts. So please unmute the microphone and feel free to ask the question if you have. So at the first, I'll start from the question from chat box. So the first question is asked by Dr. Sri Krishna Bhattrai. Why is the cloud measured in terms of megahertz? How is it related to density? Dr. Joshi?
Yeah, that's
Are
right.
you-
Yeah, yeah. I'm right here.
oh.
Do you hear me?
So, yeah, I'm listening.
So let me say it again. Sorry. Do you see the? Sorry. So yeah, the question was why the cloud is in megahertz instead of the although it is in density, because there is a conversion formula which can change density in megahertz. So in this formula, this is a simplified version. Ne is the number density in meter cube, where Fp plasma frequency in is in hertz. So meter cube generally there it is in 10 to the power 12 per meter cube. So if we take the square root of 10 to the power 12, we'll get 10 to the power 6. So 9 into 10 to the power 6 hertz will be 9 megahertz. So there is a conversion formula which easily changes number density to hertz, to frequency. That's the answer.
So another question is, so I just saw the ANPA USA. So I don't know the exact name of the person asking. What if your simulated distribution is far off in comparison to the real one?
Say it one more time, please.
Uh, what if your simulated distribution is far off in comparison to the real one? I think this question is asked by Navin sir.
So if the what or why? What?
What?
Okay. Yeah, if I simulate something on realistic cloud, like it will produce something, it will produce different result than the real observations. If I simulate a cloud which is far off from the observations, it will create effects which will be very far off from the observations, and that will defeat the purpose of modeling the observation.
So any question from any other audience? If you have any question, just on mute and then feel free to ask.
Hello, hello. Dr. Prince, very nice talk. I have a quick question in your slide number 22.
I
Can
would
you please go to,
I would appreciate if you can tell your name as well. Okay.
this is Rudra Kafle from Worcester, Massachusetts.
Okay, Rudra sir. Very good evening.
Good evening. So in slide number 22, yeah. So what is so is the green curve feet, or what is this green curve on the background of this data?
Yeah, it's just a cartoon. Like the green card curve is the path of the numerical satellite or the imaginary satellite that I tried to flew through the synapse data.
Okay, okay. That is not the feed to the data, right?
No, it's not a fit to the data. It's an imaginary path.
Okay. Yeah.
It's a cartoon. It's for illustrative purpose, but
Mhm.
it would be representing the path of a satellite. For
Mm.
example, for the third bin, the satellite is flying above the numerical apex altitude. In that case, the satellite will miss to detect the irregularities. For the
Mhm.
fourth bin, it is below the numeric apex altitude, so it will detect the irregularity. So this is just to illustrate how the imaginary satellite, if I perform a simulation through the available synapse data, can miss or detect the irregularities, and this is expressed in the this mathematical expression as well.
Yeah, thank you. Thank you very much.
So any other question from audience? So if not, I have one very quick question. I am not expert in that field. That's why my question may not be like very scientific, but I heard that there is zero refractive index. Somewhere I heard, is that right? I'm listening that one. So zero refractive index means how to get the reference. You are telling less than one. Is that the meaning of less than one, or there is no any like bending of light? What is the meaning of zero refractive index in your particular ionosphere
I
condition?
I think that's a very good scientific question. Thank you for that. That means the k vector will no longer propagate upwards; it will propagate downwards.
So that means it always go away from the normal, isn't it?
Yeah, I think I have to take the dispersion relation, but I think that will relate to, like, if we want to think in the like physical mathematical relationship, it will relate to the k vector, and the k vector will always refer to the direction of propagation. So I think it will no longer be reflected, meaning it will reverse the direction, I think.
Because one refractive index is we call the standard year, and then any refractive index greater than one is always bending the light to the normal. So that means less than one means it has to go away. Is my very layman thinking, so I'm not sure about that.
Okay, I have to check the dispersion relation, but it will mean that it no longer refracts. Now it instead will be reflected as the refractive index goes to zero,
Okay,
because the
thank
k
you.
vector, it no longer propagates in the direction it is propagating. Let me put it,
Hmm.
because the k vector goes zero, because
Yeah.
the k vector goes zero. Like, I have to check the dispersion relation, which I don't have handy in my memory, uh,
Uh-huh.
but I remember out of my discussion that the k vector goes to zero. It means it is no longer will be going in the direction that it is going, and it will be reversing the direction. And that's
Okay,
why
thank you.
it will be
Thank you.
changing. It will be changing direction, and it will be changing direction, and that will
Hmm.
make it reflection.
Hmm.
It will
Okay, thank you.
it will it will constitute condition for reflection.
Thank you. So any other question from the audience?
Hey, Dev Joshi Simpasupati.
Good evening, sir.
Kiran, I wanted to ask about this. What you said you did this measurement on the Marshall Island?
Yes,
Okay, that's closer to the equatorial line, right?
yes.
Does it make a difference if this the equatorial or the other side of the Earth, the cloud movement and other things? Does it matter?
It makes a good difference. It makes a very good difference, and the all is divided in regions: equatorial ionosphere, middle ionosphere, and high latitude ionosphere, because these have different. The magnetic field has different geometry, and due to the different geometry of the magnetic field, the electromagnetic phenomena in the different region are different. And in the low latitude, there are exotic phenomena because of the horizontal magnetic field lines at the equator.
So is
So
that the reason the Marshall Island was chosen?
I think so. It's that exact region. Yes, I think so. Yes,
So that lab belongs to U.S. government?
I think so. Yes, to the, I think, U.S. Army. I think, and I think that has been used for many critical missions. Many
Is that
history.
nearby like Greenland?
I
No,
don't
it's
know.
it's in the close. It's somewhere in the sea.
Uh,
It's in between US and like say Australia, right?
I think so. Yeah.
Okay.
Again, like, my advisor was trying to send me in one of the missions for such experiment, like another sounding rocket mission. I was not allowed to because of not being a US citizen.
Yeah, providing a responsibility clearance.
Because yeah, the elections were thought to be a little sensitive for a foreigner to be.
Uh,
So if this new institute was under the is an independent institute or the
It's the
geology?
it's the independent institute, and since they do defense related research, they rather operated with less fanfare.
Okay.
So they were kind of secretive. Let me put it that way.
Yeah.
So
Good
they
to
were
see
not
that Boston,
as much
good to
well
see that
known.
Boston College logo on the left hand side. That's why.
Yeah. So they are within the Boston College, but they are a separate institute, and they operate rather with very less advertisement, I would say. So they are lesser known as in the university, I would say, because they operated independently.
Yep. Okay. Thank you. Good talk.
Thank you so much.
so let's wait 1 minute. If there is no any question, we can wrap up today's presentation.
And I would also appreciate like informal feedbacks, comments on my presentation, so that I can take those in my future presentation and talk.
Yeah, sure. So I think the looks like there is no any question. So thank you once again, Dr. Joshi, for your time and science you shared today. And also thank you for the audience for your time.